Hello, dear students. Welcome to the channel and welcome to another playlist, a new playlist in which we are discussing about corona, over voltages, and such things. Right. So, in previous class, we have discussed about corona, its details, how it gets generated, what are its advantages and disadvantages, what are the factors affecting it, and we also discussed how we can get rid of corona. So if you haven't checked out that video, the link will be flashing on the top right hand side corner of your screen in the I button. Click on it and check it out. And today we are going to discuss about the over voltages. And to understand over voltages, you don't need to see any other video, so it is not in continuation. But uh, still, the basic knowledge of electrical engineering or electricity is uh, beneficial in such cases. So without further ado, let's get started with over voltages. So in power system, you will see there are several instances where the elements of this power system, like generators, transformers, transmission lines, insulators, so um, such elements are subjected to over voltages. What is over voltages? Over voltages is a basically voltages greater than the normal value. So these over voltages on a power system may cause due to many reasons, and these reasons can be lightning, opening of a circuit breaker, it can be grounding of a conductor, and most of the over voltages are not of large magnitude, but it is still important because their effect on the performance of my circuit, it will be interrupting the circuit elements, different equipments of my circuit, and even the protection devices. An appreciable number of these voltages are sufficient in magnitude to cause insulation breakdown of my equipment as well. And we all know how damaging this insulation breakdown can end up. And therefore, the power system engineers always devise ways and means to limit this magnitude of over voltage, which are produced in the control, which are produced to control their effects on the operating equipment. So in this chapter we are going to discuss about such over voltages in power system with special emphasis on the protection devices which are used for the protection purposes from over voltages. So let's first know what is an over voltage, and for that let's try to understand what is a voltage surge. So a sudden rise in a voltage for very short duration of time on the power system is known as voltage surge or transient voltage. So even though this voltage surge is a temporary in nature and it exists for very short duration, like it will exist for few milliseconds only, but it will cause over voltages in my power system. And how do they originate? So basically they originate from switching operations, and even from other causes. We are going to discuss them into the detail, so no need to worry. But by far, for the most of the times, the origin of such over voltages and the important transients which cause major damage on my equipment are caused by lightning strokes or lightning striking, right? When lightning strikes my transmission line, and when such phenomena occurs, when lightning strikes my transmission line, surge rushes along the line like flood of water rushing into the narrow valley. And when retaining wall of reservoirs, as it is as it had sudden as its head will suddenly gives way. So in most of the cases, such surges may cause the line insulators to flash over, and ending up damaging the nearby transformer, generator, or whatever equipment connected to it. So it can cause major damage. Now, for better understanding and for technicality, let's see this figure. It shows the waveform of a typical lightning surge. In typical lightning surge, what happens? Let's say I'm having voltage buildup on my y-axis. I am presenting it with term em, and I'm taking time on the x-axis, and I'm presenting it by t, and the time is in the microseconds, and voltage is definitely in voltage. So from the graph, you must have seen that the lightning is introducing a steep fronted wave, especially in the early stages. So the steeper is the wave front, the more rapid will be the buildup of voltage at any point in the network. And in most of the cases, this buildup is comparatively very rapid. Like, it lasts for hardly 1 to 5 microseconds. And voltage surges are generally specified in terms of rise time and decay time. You can see I have represented it using T1 and T2 variables. T1 stands for rise time, T2 stands for decay time. Sorry, T2 stands for, yeah, decay time. Decay to the half of the peak value. So, like, you can say the rise time. What is rise time? So the time by which voltage is continuously rising, it is not falling off. So at the instance when voltage starts to fall off, the decay time starts. Time before it will be rise time. Now what will be the decay time? Decay time will be the instance from where voltage starts to decaying till the voltage reaches to half of its peak value. That is the decay time. So let's say if I'm having a signal, or if I'm having a lightning surge, and 1 by 50 microsecond surge is one which is reaching the maximum value in 1 microsecond, and it is decaying to half of its peak in 50 microsecond. So what will be my rise time? It will be till the instance it is reaching till top value. And what will my decay time? 50 microseconds, right? So that is the voltage surge. Now let's see what can cause voltage surge. What are normally causes of voltage surge? So the any type of over voltages on my power system may be broadly divided into two main categories. One is internal causes, and second will be external causes. And what can be internal causes? Internal causes can be switching surges, different type of switching which takes place into the power system. Insulation failure can be the cause, arcing ground can be the cause, and resonance condition can also be cause. And external and most destructive cause of overvoltage is lightning. Now, normally the internal causes do not produce such large amount of magnitude. So the surges because of these internal causes are uh, hardly manages to increase the system voltage to twice to the normal value. And generally these surges due to internal causes are taken care by providing insulation of the equipment in power system. But the surges due to lightning strike are very severe and may increase the system voltage to several times the normal value. And if my equipment in the power system is not protected against these lightning surges, then these surges may cause the considerable damage as well. And in fact, most of the devices which we are using in the power system are the protective devices which are provided for the protection against over voltages, like lightning strike, basic lightning strikes. Now let's see internal causes into the detail. First one is the switching surge. So the internal causes of overvoltage on my power system are primarily because of oscillations set up by the sudden change into the circuit conditions. And these circuit conditions, like circuit change, may be normal switching operations such as opening a circuit breaker, or fault condition like grounding of my line conductor. Such condition causes it. And in practice, normal system insulation is suitably designed to withstand such surges, so it handles that. So let's first see switching surges. So the over voltages produced on the power system because of switching operations are known as switching surges. We all know that. And let's see few cases of it. First case is of an open line. So during switching operation of my unloaded line, traveling waves will be setting up, which will produce over voltages on my line, which you can see in this figure. So when unloaded line is connected to the voltage source, as you can see, a voltage wave will be setting up, which will travel along this line. And on reaching a terminal point, let's say this terminal point A, it is reflected back to the supply and without change of any sign. And because it is reflecting back without any sign change, my voltage will get doubled, which means voltage on the line will be twicer than the normal voltages. And if I try to find the RMS value of my supply voltage, then instantaneous voltage which the line will have to withstand will become 2 into root 2 into RMS value, or 2 into root 2 into E for this case, because supply voltage is E in our case, right? So this voltage is most of the times of temporary nature, and it is because the line loss are attenuated the wave, and it is it lasts for very short amount of time. The line will settle down to its normal supply voltages. And similarly, if unloaded line is switched off, then the line will attain a voltage of 2 root 2 into E for a moment before setting down to the normal value. Now let's see the second case, that is the case for loaded line. First one for the unloaded line. So second one is for the loaded line. So when over voltages will produced during the switching operations of loaded line, let's take a loaded line, and let's say it is getting interrupted suddenly. So what will happen? This will set up a voltage of 2 into its impedance into current across the break, across the switch, right? Where what will be the value of current? It will be instantaneous current. And at the time of opening line, whenever you open that line, your impedance will be the natural impedance of line. So for example, suppose if I'm having a line which is having impedance of 1000 ohm, and it is carrying current of 100 rpm 100 amperes, then the break current at that moment will be the when current will be maximum. So voltage across this breaker will be, when you do the math, 2 into root 2 into 100, because 100 is my voltage, 100 is my current, into 1000 divided by 1000, so it will get cancelled. So you will be left with 2 root 2 into 100, which means 282.8, right? Because what is the value of root 2? 1.441, double of that, 2.82 into 100, so 282 kVs. So if Vm is the peak value of voltage in kilovolt, and maximum voltage on which line may be subjected will be Vm plus 282 kilovolt. Understood? The third one is the current chopping, and it is very much famous. I bet you might have heard it. Like current chopping is a result in the production of high voltage transient across contacts of air blast circuit breaker. And unlike oil circuit breakers, because we are particularly talking about air blast circuit breakers, we are not talking about any other circuit breakers. So unlike oil circuit breakers, which are independent for effectiveness of their magnitude of current which being interrupted, air blast circuit breakers retain the same extinguishing power irrespective of the magnitude of this current. So when breaking current will be low, which means transformer magnetizing current will be low, with my air blast circuit breaker, the powerful deionizing effect of air blast will cause the current to fall abruptly to zero value before my natural current hits zero value. And because of this phenomena, your current chopping will occur, and it will produce high transient voltage across my breaker contact. Because current is falling suddenly, so voltage will rise suddenly. So that was about switching surges. Now let's see what will happen with insulation failures case. So the most common case of insulation failure in power system is when conductor gets grounded, as you can see in this image as well. And you can also call it insulation failure between line and earth as well, because my basically my conductor is getting grounded. So it will cause over voltages. And for this line, let's say I'm having a line which is having potential E, as you can see in this line, and my earth is at potential X, and earthing of this line will cause two voltages of minus E to travel along this QP path, travel along this XQ path, and X and this XP path, which will contain current. You can see here what is the current, minus E divided by Zn and plus E divided by Zn, right, respectively, for both of these XQ and XP. So both of these currents passes through the point X to the earth, so that current to the earth will be 2 into E divided by Zn. So current will be twice, and it will fail the insulation, it will cause over voltages. Third point is the arcing ground. So in the old days, earlier days, like back in the 19th century, or even in 20th century, the neutral of my three phase line was not ought to gain two advantages. So firstly, in case of line to ground fault, the line is not put out of an action, and secondly, the zero sequence current will get eliminated. So it will result in decrease of interface between interface with communication lines. Then insulated neutrals will no problem with short lines, and comparatively will have low voltages. But when the line are long and operating at high voltages, there will be serious problem, and this problem is arcing ground. So arcing ground will produce severe oscillation of 3 to 4 times than normal voltages. So how you can define arcing ground? Arcing ground can be defined using this definition: the phenomena of intermittent arc taking place in line to ground fault of three phase system with consequent production of transient is known as arcing ground. And this transients which is produced because of arcing ground are cumulative, and that is the most destructive thing about them. They may cause serious damage to the equipment in the power system by causing the breakdown of my insulation. So what do you do to prevent this arcing ground? So in order to prevent this arcing ground, uh, we can do the earthing of neutral, and we can prevent the arcing ground. Another point is the resonance, and we all have studied resonance since class 10 or class 12. I don't remember what is the resonance condition. So resonance condition is same old for electrical systems. When inductive reactance of my circuit breaker will become equal to the capacitive reactance of my circuit breaker, it will cause resonance condition. And under resonance condition, the impedance of circuit will be equal to the resistance of the circuit, and power factor will become unity. So the resonance will cause high voltages in this electrical system, and in the usual transmission line, normal transmission line, the capacitance is normally kept very small. You must have seen it until now. So the resonance will rarely occur, right? At least at fundamental frequency, it will. There are very faint chances of occurrence of resonance condition. But if generated EMF wave is distorted, and the trouble of resonance can occur when generator EMF wave is distorted because of the fifth harmony, seventh harmony, and all these higher harmonics, right? Especially in underground cables. In overhead, it is almost not possible. It's almost zero chances of occurrence of resonance. Next point which we are going to discuss will be lightning. Now, basically, what is a lightning to you? What do you think when I pronounce the term lightning? So, an electrical discharge between cloud and earth, or between earth, between clouds, between two clouds, or between charge centers of the same cloud, is known as lightning. So, basically, it is a huge spark which takes place when clouds are charged to the high potential with respect to earth or neighboring clouds, or even the same cloud, different charge centers of the same cloud. And the dielectric strength of uh, neighboring medium gets destroyed. At that time, lightning surge or lightning strike happens. And there are several theories which exist to explain how this cloud acquired the charge. And most accepted one of them is that during uprush or of warm air from the earth, the friction between the air and the tiny particle of water causes charge buildup. And when drop of water are formed, the larger drops become positively charged and the smaller drops become negatively charged. So when the drops of water are accumulated, they form clouds, and hence clouds may possess either a positive or a negative charge depending upon the charge of drops of water they are containing. So the charge on a cloud may become so great that it may discharge to another cloud or to earth, and we call this discharge as lightning. So the thunder which accomplishes lightning is due to the fact of the lightning suddenly heats up my air, and therefore it causes my air to expand, and the surrounding air will push the expandable air back and forth, causing wave motion of air, which we recognize as a thunder. Now let's see how does this lightning gets formed, right? Let's discuss the manner in which lightning discharge occurs fundamentally. So when a charged cloud passes over passes over an earth, it induces equal and opposite charge on the earth below, exactly below that charged cloud. Now that you can see from this image, see, we are having a charged cloud, and see, it is also giving you equal and opposite charge to the earth, right? So as the charge acquired by cloud will increase, the potential between cloud and earth will also increase, and therefore the gradient in the air will increase. And when this potential gradient is sufficient to break down my surrounding air, the lightning stroke will start, right? And what will happen when such thing happens? So as soon as the air near my cloud breaks down, the stream called leader stream or pilot stream starts to form cloud towards the earth and carries charge with it, as you can see in the second figure. And this leader stream will continue its journey towards earth as long as the cloud from which it originates feeds enough charge to it, maintaining gradient at the tip of the leader stream above the strength of the air. And if this gradient is not maintained, then the leader stream will stop and the charge will be dissipated without the formation of complete stroke. Or in other words, you can say the leader stream will not reach the earth exactly. Right? It will not reach earth exactly. So see the first figure here. What you can see, the leader stream is being unable to reach the earth as a gradient as it is, and as it ends, cloud will not be maintained above the strength of the air. So it is not reaching towards the earth. And you can also note that the current in the leader stream is very low, and its velocity of propagation is about around 0 to 0.5 of the velocity of light. So it is very quick and it is very luminous, right? It is very luminous of leader as it also varies. In many cases, the leader stream will continue its journey towards earth, and until it makes contact with the earth or some object on the earth, it will keep moving. Not in every case, but some cases. And as the leader stream moves towards the earth, it is accompanied by the point of luminance which will travel along, right? And it jumps, giving rise to the stepped leaders. So you can see those side streams or stepped leaders here, and that is your actual leader. And the velocity of the step leader will exceed one sixth of the light, and distance traveled in the one step will be around 50 meters. And you can also note that the step leaders have sufficient luminosity and will give rise to the first visual phenomena of discharge. Now let's discuss about the third point. The path of this leader stream is the path of ionization and therefore of complete breakdown of insulation. And as the leader stream reaches the near the earth, the return streamer will shoot up from the earth to the cloud. So you can see that in this third figure, a return streamer is shooting up towards the cloud, and it will follow the same path as the main channel of the downward leader. And that action can be compared with the closing of a switch between positive and negative terminals. The downward leader will have negative charge, and it will return the return streamer will have positive charged. Sorry, downward leader will have negative charged, and return streamer will have positive charge. So this phenomena will cause sudden spark which we call lightning, and with the resulting neutralization of much of the negative charge on the cloud, any further discharge from cloud may have to originate from some other portion of that cloud. So we have to note few points about lightning discharge. The first one is the lightning discharge, which usually appears to the eye as a single flash, is in reality made up of number of separate strokes that travel down the same path, and the interval between them varies from 0.0005 to zero point 0.5 seconds, so milliseconds. So each separate stroke starts as a downwards leader from the cloud, and it has been found that 87% of the lightning stroke result from negatively charged clouds, and only 30% originate from the positively charged clouds. So most of the times lightning strokes are produced by negatively charged clouds. It also has been estimated that throughout the world the occurrence of about 100 lightning strokes per second. So it's not rare, it's just not frequent in your region. And lightning discharge may have current in the range of 10 kiloampere to 90 kiloamperes, and that is why it is very destructing. So we will keep today's lecture till here. Next time in the next class, we are going to discuss about the type of lightning strokes and how they can cause damage and what steps can we take in order to prevent the lightning stroke. So thank you very much for listening. I will be seeing you in the next class. Till then, take care of yourselves and goodbye.